Okay, so what we're going to do today is we're going to talk about linear regression. And the point of linear regression is we want to examine the relationship between two variables, such as, is there a relationship between the temperature in the room and the number of chirps of a cricket? Okay. Or is the lack of sleep associated with high stress? Okay, or is there a relationship between, say, your ice cream carton size and the price? So association, two variables are associated, and knowing the value of one variable tells you something about the value of the other variable. Okay? And the variables should be measured on the same, what some books call the cases of the same person. So like if I want to see if there's a relationship between height and weight, I won't measure my height and someone else's weight. That's not really going to tell me much. Okay? So we measure everything on the same person. Okay, and often we're really interested in knowing not just do they have a relationship, but do they have a linear relationship. So we have our response variable, which the response variable measures an outcome of a study. Often we will call this the dependent variable. And the explanatory variable explains or causes the change in the response variable. Now, I'm kind of assuming that you all had to do something like this in high school or 1050 or something, and most of this is probably familiar. So you can stop me if I go for something too fast. Okay. Sometimes we have an explanatory variable, and sometimes we have our explanatory and response variable, and sometimes we just want to see if they're related. So you don't always have the explanatory variable, and that's okay. So like, for example, Sherry's a college student aid officer. She looks at data on college graduate debt and their stress levels to see if they're related. She's not trying to make predictions at this point, and so she doesn't really have a response and explanatory variable. Whereas like Jim's a sociologist, and he wants to use the amount of debt to explain the stress levels. So for Jim, what would be his explanatory variable? The amount of debt. And the response variable is his stress levels. Okay. And also, so sometimes you may not have your explanatory response, sometimes you do, and also sometimes people might switch them. So I might be interested in predicting one thing, and you might actually be interested in predicting the other thing, and that's okay. Okay, so we make scatter plots. You should have all seen a scatter plot at some point in your life. But it shows the relationship between two quantitative, remember quantitative is another word for numerical, variables measured on the same individuals. The explanatory variable has to go on the horizontal x-axis, the response variable goes on the vertical axis. Of course, if there's not an explanatory variable, then it doesn't matter which one you put on which axis. So for example, we have that botnets are used to send spam. So here's some data on the top. Botnets, and I said make a scatter plot, but I already made one for you. So if you don't know how to make a scatter plot, come back and study this later. But it's just plot your coordinate pairs. What we care about more, because I'm not going to ever make you make a scatter plot by hand, okay, but we really care about examining the scatter plot. So we want to look for overall patterns. So is there a shape of the pattern? What is the direction of the relationship? Does it seem to be going up or down? Okay, so like two variables are positively associated when high values of one variable occur with high values of the other variable. This would mean we have positive slope. Okay, and two variables are negatively associated when high values of one variable accompany low values of the other variable, which would be negative slope. So we want to know what's the shape of our pattern. Does our pattern seem to be going up or down? Okay, what is the strength of the relationship? And also we'll look for any data points that don't seem to fit with the rest of the data, such as outliers. Okay, and we already know that outliers are just values that don't fit with the overall pattern. Okay, so if we look at our botnet scatter plot again, okay, do our points seem to follow a pattern? Okay. It could be kind of linear. Now when I ask you how strong do you think the relationship is, you're all saying kind of linear, so you feel like the relationship is or not super strong. So I think it could be linear enough, but it's not necessarily really strong. The points aren't really all that close to the line. Okay. Is it going up or down though? Up. It is a positive slope, so positive association. And any outliers? It doesn't really seem to fit with the pattern. I mean, maybe if you took up that one, the rest would be closer, but it's still not necessarily so far off that I can tell for sure if it's an outlier. Like, maybe an outlier. I'm still going to guess maybe, but probably not. It's definitely the one that's furthest away from the rest of the pattern. Okay, so this is far from the rest, but it still follows the same pattern. Okay, so maybe an outlier, not necessarily so big that I can tell for sure though. So for this next one, here's our scatter plot of debts for 30 countries in 2006 and 2007. Now, just thinking about that, so for each country, you just measure their debt in 2006 and the debt in 2007. Would you expect the debt in those years to be pretty highly correlated? Okay. If you have a debt in 2006, your debt shouldn't change that much from 2006 to 2007. Okay. And so, just like you might expect, it looks like our relationship is pretty strong. Those points are pretty close to the line. So, it doesn't seem to follow a pattern. Well, it does seem to be linear. It looks like it is going up, so it would be positive. What about outliers? I would say definitely not, so no outliers. And how strong do you think this relationship is? Okay. I think it's very strong. There's very few situations where you're going to get points that close to the line. Okay. So for our next one, we have two variables. So for us to analyze 128 countries, two variables are unemployment rate and gross domestic product per capita. So here's our scatter plot. Okay. So do the data points seem to follow a pattern? Okay. They kind of follow a pattern, but isn't that pattern a line? Okay. So kind of a curved pattern. Is there a positive or negative relationship? Negative. But it is definitely not a line. Okay, and this happens often in practice. You go out and you look at a data set and it comes back and it's not a line. But that doesn't mean that you don't want to analyze it. Okay. So one of the things that you can try to do is transform data and try and make it look more linear. So for example, this is what happens if you take the log of the GDP per capita. So you still plot your unemployment here, but then you do the log of the gross domestic over here. Notice it doesn't look exactly linear, but does it look a little bit better? Okay, so not perfect or close to perfect, but a little better. Okay. And again, this is something we won't learn how to transform in this class. If you ever take Stats 5100, it's a whole class on linear regression, and you'll learn how to do this pretty well. But for now, just know if you're ever in classes, you can go look up how to transform data. No? So for our next thing, we want to be able to measure the linear relationship between two variables. So basically, we want to see how close are the points to the line and measure that relationship somehow. Okay, so when you look at these sets of data points, okay, from here to here, can you tell which one of these relationships seems stronger? So from just between these two, the first two, which one do you think has a strong relationship? Okay, so the first one, okay, what about these two? So you know the second one? Now, who here knows about correlation from another class? If you know about correlation, raise your hand. Okay, so not everything you do. So as next to the second one looks stronger. Okay, but they're actually the same. Correlation, which we'll learn about on the next page, so if you don't know what correlation is yet, we'll learn about soon. So sometimes it can be deceiving just looking at it with your eyes. Okay, so something looks stronger, but they actually have the same correlation, so they have the same mathematical strength of relationship. What about the last one? What do you think about the last one? Which one looks like a stronger relationship? Yeah, the second one looks stronger, but it's the exact same data set. We just changed the scale. Okay. And so we learned from this that we can't really tell how strong the relationship is by eyeballing it, okay? Or at least not very definitively. So we need to have a more mathematical way to define the strength of our linear relationship. And the way that we do that is with correlation. So correlation then is not only the strength, but the direction of our linear relationship. And this is our formula. So we take each x value minus the x mean divided by the standard deviation of the x's times each y value minus the mean over the standard deviation of the y values. Add them all up and divide by 1 over n minus 1, where n is like the number of people that you measure. Okay. We're never going to calculate this by hand, or which is a software. Okay. For correlation, it doesn't matter which variable is explanatory, which one is response. Correlation can't tell the difference. Okay. Notice it's because multiplication is commutative, so it doesn't make a difference in the formula. Also, we have to have continuous numerical random variables. This isn't going to work for categorical variables. It needs to be continuous. Okay. The correlation R does not change if you change the units of measurements. So if we change from pounds to kilograms, it won't affect our correlation, which is really nice. Let's see. Positive values of R indicate a positive relationship or association. So positive values of R mean you're going to have a positive relationship or a positive slope. Negative values of R indicate a negative relationship. And the correlation R is always a number between what? Anyone that's taking correlation, or knows that correlation is between what two numbers? Okay. Correlation is actually between -1 and +1. Okay. So again, because the negative values will mean you have a negative slope, positive values mean you have a positive slope. A correlation of 0, so if you have a perfect correlation 0, that indicates that there is no relationship between the two variables. They don't affect each other in any way. They don't move together. It's just absolutely no relationship. Okay, values of R near 0 indicate a very weak linear relationship, whereas values of R near -1 or +1 indicate a very strong linear relationship. That would mean that the points are very close to our straight line. Also, correlation is very influenced by outliers. You could have points very close to a line, throw in one outlier, and your correlation will go down by quite a bit. And this part is very important. We can only use correlation to measure the strength of linear relationships. So a lot of people will just plug it into the computer and look at the correlation and say, oh, I got a correlation of 0.9. And it looks really good, and then if they actually looked at the data set, it might be a really definite curve. Okay? So the computer doesn't check first to see if it's linear or not. That's not built into it. You have to look at a scatterplot as the human, make sure it's linear before you do correlation and linear regression. So I have some examples of data sets and their correlation just so you can kind of see them. Okay, so here's two different examples with a correlation of -1. Notice this negative slope. Two different sets with a correlation of -0.92, -0.63. So -0.27. Notice that -0.27, it's hard to even tell that there is a linear relationship there. At 0, there's no pattern. Okay. Even a correlation of 0.44, like in this one, it's kind of hard to tell if there's a linear relationship. These two seem a little more definite now. Let's see, correlation of 0.87, and again, three different sets with a correlation of 1. Any questions to this point? So this is where your book starts, with a simple linear regression model. Okay? So if we had two continuous variables that have a linear relationship, then we could use our linear model where y equals a beta naught plus beta 1x. Okay? Now you are used to seeing equations of lines that look like this. Right? That's the equation of the line that you used to from all your math classes. The reason we changed it all for betas is that we might want to do multiple linear regression, and so you might have like 5 different variables, so plus beta 2, y plus beta 3z, etc. Okay, so that's the reason that they switched to betas here. That we have beta 0 plus beta 1x. Now in a perfect world, with no outside influences, no variation from person to person, we would have this perfect model, and all the points would fall exactly on a line. Okay? In practice, we don't live in a perfect world, and there's a lot of natural variation, and points don't fall exactly on the line. It's very rare for points to ever fall exactly on a line. Okay? So instead, the way we're going to model it is we use our simple linear regression model. And here it is. Okay? So yi means our actual observed value of our response. So this is our one individual y value. And is equal to our intercept plus our slope times that one specific x value. Okay? So each specific x value would map to a specific y value. Okay? Plus this little epsilon. What do we use epsilon for? If it's ever come up before. Here. Okay? So basically, because our points aren't exactly on the line, we say, okay, well here's where the point should have been on the line, here's where the actual point is, and this is how far it's off. So the error term is how far each point is from the line. And so we build this into the model, realizing that the points won't be exactly on the line. So yi is where it should have been on the line, plus or minus an error term. Okay? So again, beta naught is our intercept parameter. It's the average value of y when x is 0. And oftentimes, so our intercept is necessary to identify our line. You can't draw a line without an intercept. But sometimes it doesn't give us practical information, and we'll see examples of that as we go through. Beta 1 is our slope parameter. So beta 1 represents the change in the average of y for every 1 unit increase in x. And it's just, go back to your 1050 definition of slope of y is over 1. So if x goes up by 1, we expect y to go up by whatever your slope is. Okay. As long as our slope isn't 0, then we have x and y are linearly associated. Or we can also say that they are correlated. And we'll talk more about that later for why if the slope is not 0. Okay, a few things about the error terms. Okay, our error terms, epsilon 1 through epsilon n, are independent. Okay, so these are kind of our assumptions. They're all supposed to be independent, so the error point for one person shouldn't affect the error for another person. And the error terms come from a normal distribution with a mean of 0 and an error variance of sigma squared. Now, since your independent error terms come from a normal distribution with mean 0 and sigma squared, then the values y1 through yn are observations from the independent random variables. So we have our random variables y with the I on them because we have each possible y value as its own random variable. It comes from a normal distribution. The expected value is the intercept plus the slope times the x value. So basically what the value is on the line. And the variance is that sigma squared. So for an expected xi value, so for a specific xi value, the expected y value is, well, just plug the x value into the line, and it's what you would get. That's where you expect your y value to be. And the variance of the yi values of that specific xi value is sigma squared. Notice here that there's nothing in this formula that has an I on it, which tells you that the variance for the y values should be the same at every different xi value. Okay? Which is what we call constant variance. That will come up later. Okay. So here's our example. This is why we watch the movie. So crickets make their chirping sounds by rapidly sounding one wing over the other. The faster they move their wings, the higher the chirping sound that is produced. Scientists have noticed that crickets move their wings faster in warm temperatures than in cold temperatures. Therefore, it's possible to use the cricket chirps per second to find the temperature of the air. So, in the clip we watched, he knew the temperature and wanted to know what type of cricket it was, so it was kind of the opposite. Now we know the chirps per second, not chips per second, and we want to know the temperature, so we can actually use the crickets to predict the temperature. Notice when you look at this line, you can't tell super well, but are all the points exactly on the line? No, and in fact, sometimes you have double points. So like right here, we have one point, and then we have another point right underneath it. So that means that we could have had two different crickets that both chirped 20 chirps per second, and the temperature was slightly different when they did it. Okay, and so it's just kind of that thought of, okay, my y values can vary. So even if you have the exact same x value, it is possible to get different y values from it. But these points are all very close in line, very close in fact. Okay, let's see, chirps per second temperature can be related through our following regression equation. So y equals 26.346 plus 3.24x. With our error terms distributed normally with a mean of 0 and variance of 0.94. So what is the expected temperature when the crickets are chirping at 20 chirps per second? So how would you find your expected temperature? Yeah, there isn't necessarily, we just have to plug it in. So in this case, our x is 20, and all we have to do is plug it in. So 26.346 plus 3.24 times 20. So we just plug in our x value into our equation. Equals 91.146. Okay. And this is our expected. Does that mean every time a cricket chirps at 20 chirps per second, it's going to be exactly 91.146 degrees? Okay. No, but overall, if you looked at this many times, the average or the expected value would be 91.146. So remember, this is our average. Not every individual value, but the average of the y values for 20 chirps per second will be 91.146. What about how much does the expected value of the dependent variable, that's temperature, change when the explanatory variable increases by 1? What does that sound like is asking this? The slope. So if chirps per second increase by 1, we expect temperature to increase by what? What is my actual slope? So at this point, you should know from your math classes that your slope is always the number in front of the x value, so 3.24 degrees. So if chirps per second increases by 1, we expect our temperature to increase by 3.24. Now, this is a good place just to point out, are the crickets chirping causing our temperature to change? Okay. No, that would kind of be silly, and that's a very big thing in linear regression is people try and show causation, and you can't. We can't show that crickets cause the temperature to go up, but if we know what the crickets are chirping, we can predict the temperature. So remember, it's just getting this information to predict, we're not showing that it causes a change.